Hey there. Well, it's time to get on to case 5, the last model from the textbook that I'm going to cover. In the context of the textbook, I am going to continue to expand on this over the last couple weeks of the semester. Where we had left off 2 videos ago was actually with case 4, which this is the one that I did the fake estimate of within Excel. And one of the last things I talked about in the video was there still is some serial correlation here in the residuals. Now, there's a good deal of, I wouldn't call it art, but I would call it craft in interpreting residuals, because it's certainly possible that in the real world the macroeconomy is hit by repeated shocks in one direction. We should not be dismissive of that just because we get a bunch of negatives or a bunch of positives in a row. Okay. What I am concerned about here is maybe too many instances of a bunch of negatives in a row or a bunch of positives in a row. Not necessarily the size or the length of them, but the fact that there's more in that range of 2, 3, 4 row runs in a row than maybe something that's, say, 10 rows or something like that, that just occurs singly. In any event, with time series, these things are easy to check. If you believe there's serial correlation in your residuals, the easiest way to deal with that is to add a lag-dependent variable. Now, we've already done this when we went from case 1 to case 2, and it helped a lot. Now what I want to do is go from case 4 to case 5 by adding a lag-dependent variable. But remember that the dependent variable now is the differences of the logs, not the log levels themselves. Okay, so this is the model that is in page, sorry, I had it on the right page and I turned away from it. Um, 230 in your handbook. 230 in the one in front of me, I believe that's 2 pages ahead in yours, 232. Okay, so both case 4 and case 5 use the dependent variables, the differences, but that amounts to imposing a unit root or stochastic trend on the model. So in Excel, that's how you impose that restriction. In more traditional econometrics programs, you actually can just do that with code. In any event, what we're going to do is go back to data like we always do, and I'm going to rewrite my data set. So I'm going to go back over here where I have difference logs from the other day and copy those over here, and then put lagged version of that right next to that. And so that will put this N13 right there, and I can copy that down the rows like so. And that didn't actually work, so I'm going to go back here. I don't think my formula was robust, so my formula was based on J13 minus K13, and when I copied that formula with relative references over here, I got L13 minus M13, and that's a mess. So let me just code this by hand. We'll make this equal to J13 minus K13 and copy that one row down, and then I'll make my life easy and make this one J13 minus K13 as well. Now, because we have a lag in here, we're going to lose that first observation, and Excel is going to hate having a missing observation. So I'm just going to take these labels and copy them down one row like so. And because of the way that I set this up, this is all still copyable down to the bottom like so. And then I just run a regression. So this is an AR1 regression. Remember, case 3 was an AR1 in the levels, and that told us that we needed to restrict it to a unit root. This is an AR1 in the differences, and the differences means we've already incorporated that unit root. So we're adding on to case 3 and case 4 here. Oops. Got to go to data and data analysis. Choose the regression tool. My y variable is just those difference logs. And there we go. That is our AR1 model and differences. That is case 5. So let me clean this up a little bit. Make everything wider, center everything, reduce the number of digits I show to a more digestible number. And then last but not least, always add a label. So this is regression of differenced logs of real GDP on a lagged dependent variable. And I guess because we do differences in the lag, it's now 1931 to 1996 is what we have available to us. Okay, and let's look at what we got here. Okay, so our coefficient is 0.535. That tells us that we have pretty significant serial correlation. It is significantly different from 0. We can see that with this small standard error and the t statistic here, or by this 95% confidence interval over here. And it's also significantly different from 1, so we don't have a unit root problem either. So we have something we should include because it's not 0, and we have something that's not 1 creating us additional difficulties. Now, one of the nice things about time series models is simpler is often better. And so this is actually a pretty good rugged model for how real GDP actually works. Let me call this case 5 down here. And let's construct the residuals to this. So I'm going to go back over here and I'm going to copy my, let's see, I'm going to bring my dates because I like my dates. And we'll put a year over a label for that. And I'm going to bring my 2 variables from my regression. And you know what? I'm going to take both of those rows now. And it's dropped my 3-digit formatting, so I'm going to add that back in. And I copied these as variables rather than formulas, simply so I could avoid any problems with the mathematics. And now what we can do is create a fitted value and a residual. So the fitted value is, as usual, the intercept, and I will put $signs on that, plus the slope. I'll put $signs on that. Oops, went too quick there. Put $signs on that, and then multiply the whole thing by the lag in the cell directly to my left to get that. And then my residual is my actual value in B22 minus my fitted value in D22 there. And so we get a negative residual in 1931. That makes a lot of sense. And then carry this down to 1996, like so. And one of the nice things here is if we go up and look at the standard error, it's a significant improvement in the standard error, getting it down to about 3.8%. And if we go down to the bottom of our row here, our residuals are even smaller. We've got to say a 0.007 and a minus 0.0011. Okay. Well, the 0.07, these are a little bit, tad bit larger than these ones over here. My memory is a little bit bad on those. Okay. But in general, they have to be smaller in order to get the standard error smaller there. Okay. They also match up fairly well with our recessions. Okay, they now get a fat weak area here around the 1990 recession, which was kind of a dragged out weak period, and it even goes into 1993 and then even into 1995, which is consistent with the first term of the Clinton administration being kind of weak. Okay, it gets a soft spot in 1985-86. We thought we were pretty close to a recession in there. Okay, gets a large shock in 1982, a large shock in 1980, also picks up the weakness in 79 as the Carter administration's expansion was starting to fall apart. Okay, gets a big shock in 1974, which was just a bad year all around. Okay, picks up 1960, gets 67. Of course, if you go back, that's not a recession year, but that was a year when the economy was pretty weak. We tend to romanticize now the protests in the 1960s as being political, but they were slightly economic as well. Go back here to 60-61, again, an obvious recession, another obvious recession in 58, another one in 54. Okay, in general, these look like pretty good shocks. Okay, and they give us a sense again of what a typical sort of shock is in size. Remember, over here the other day we estimated these as being maybe 40-50 billion dollars, and these are kind of in the same range here. Okay, so this gives us our AR1 model indifferences, which is equivalent to an ARI11 model in levels. Excel can't actually estimate an ARI11, but an econometrics package can, and in the appendix I show you that Stata can do that. But Excel can mimic it by imposing the restriction at the level of the data and then running the restriction on the restricted data. Now, also having this, it's worthwhile to think about what would this look like if we actually had a shock. Okay, so I'm going to go up here and I'm going to take the fitted values, okay, as our predicted values, and I'm going to go copy these over here. So this is going to be D22, and so this is my fitted value repeated, and I'm going to put a fake shock in here and make that 0, and I'll call this my fake growth rate here and my fake level here, and we'll build up what this actually looks like. Okay, so the fake growth rate is the sum of the two of the things to the left, so that's G22 plus H22. And then the fake level adds this on to what log GDP would have been in 1930. And we still have that back in the data. We can go look at that. So that was the 6.923 that we have here. So I put in the 6.923 plus, actually, you know what? I want to make this robust going down the road, so let me actually link this back to a point in the data. So we'll go back to there, okay, and then add in our fake growth rate, or our fake growth rate, excuse me, to the left. And then down here, one cell down, my what I'm going to put in here is actually J23 plus, excuse me, J22 plus I23. So that's going to be the level of the previous period plus the growth rate in the current period. And copy this down, and that ought to work. Copy this down too. Okay, and now I'm ready to copy this whole thing down here to the bottom. And I'm ready to do some graphs, show you what this thing's looked like. Now I should have given myself a year column here. I did not, so let me move it over one and add the year column in here again. And so this is A22. And we'll put a big fat shock, say right in about 1960. just like we did in video 6, I believe it was. Okay. You can see that that causes growth rates to go up drastically, and it also causes the level to bump up. And this didn't work for some reason. I see the mistake, but maybe you guys don't. Ah, I know what it is. I'm using the actual fitted values instead of what's up here. Okay, so the way that I want to build this based on the regression is I want to make this, let's see here. I will keep the actual growth rate here. This whole column here is wrong, so I'm just going to delete it. Okay. And I'm not going to call this the fitted value. Let me call this the fake growth rate. And to get this to work, I want to start out with the real growth rate. So this is actually what is in B22. And then what I want to say here is that the next growth rate is B17. Whoops, didn't like that. B17 $, okay, plus B18 $, times the previous period's H22. And copy that down. And then go back and put my big fat shock in 1960 like so. And still didn't work. Because you know why? When I put this formula, I based it on the cell immediately above me, okay, which is correct, kind of, okay, but I want to be able to insert these fake shocks and have them actually affect the fake growth rate, so I need to match to this growth rate over here. Okay, so I'm going to call that J22 instead of H22 and copy that one down. And that's what I wanted to see. Okay, so the shock pushes up the growth rate for a period, but then it continues to push up the growth rate for a period after that. So I'm getting the autoregressive behavior that I expected. Okay, so now we create the chart to go along with this. And do the same thing I did yesterday. It's easier to create a big chart and delete out data that I don't want. Oops. And there we go. And so this is the behavior of our model now with a large shock to growth rates. So this is an AR1 model that's going to have some persistence to the shocks, but because the coefficient is less than 1, they're not going to be permanent. So you can see here that we're a little bit above 0, so that's my typical growth rate of about 3%. And then we have the shock here, and the shock ends up persisting for a period of several years after. And we can see that in the data. The big shock of 2 bumps up the growth rate right away, keeps it up for a year, 2 years, 3 years, 4 years, 5 years, 6 years, 7 years, 8 years, 9 years, 10 years, before it starts coming back down to the normal of 0.35. Now it gets down pretty close to that, but that's saying that those shocks are fairly persistent. I mean, this is a big shock, but even so, it takes 10 years to fade out. That's what our estimates are telling us, okay? Now we can do the same thing to get the effect on the levels. And again, I will generate a graph that's too big and then use what it's good at, or what Excel is good at, delete the extras. And ta-da! We have the pattern of the shock on the level of GDP. And you can see now that instead of a jump straight up like we had before, we have some curvature to it. Okay? So the full effect of the shock on the level is not felt right away. The full effect of the shock on the growth rate is not felt right away. It fades out. Okay? But it fades out at the rate, if you go up to the regression here, that 0.535 means it fades out about half of its size every year. Now that shock of 0.80 of 2 was relatively large, when at the end here what we're getting is shocks of 007, 001, 009, 007, 019, minus 02. So really a much more realistic shock might be something like a big shock might be 0.02. And what we see is almost no effect on the level. Okay, that actually is okay, because if you think about going back to Barrow in the first week of the semester, that's what his GDP model looked like. Okay, if we look at the growth rates, we get a bump up in the growth rate that lasts for a little while but not forever. Okay, because the shock is not too large. Now, in the real world, we don't get shocks in isolation like that. When we get something like a recession here, where am I here? 1981-82, okay, a sequence of bad years here, okay, looks something like this. So let's take out that zero, take that out and put that zero back in, and let's isolate 79 to 82, okay. This here is catching the initial growth rate in the Great Depression before it settles down to a normal level after a while. So that's kind of expected by the way that we start our data set with a bad period. Okay, come down here, okay, and put in my minus 0.014 to match up with 1979 there. Okay, gets us a little shock. But in the real world, the shocks add one on top of the other, so then we get that followed by a minus 0.035, okay, which looks like this. But then we have a little positive shock in 1981, so that's the 0.010 here, okay, and you can see how that changes the curvature up at the top. And then we get a big negative shock, 0.048 in 1983. And we start to get a pattern here that looks like our recession in 1980, followed by a little good period in 81, and then a worse recession in 82. And you can see here what it does to the levels. It creates that little dip right there. Okay, it is again still consistent with Barrow. Part of the reason for this is the scale along this axis here. In the sort of time frame that we're talking about, 80 years here, one bad recession is not a horrible thing. Okay, but I don't encourage it, but we can adjust this axis here to accentuate those sort of effects. Make this, say, go from 6 to, let's leave it from 6 to 9. Okay, so we can see our double dip recessions here. They actually don't call this a double dip. They think of this as two separate recessions. Okay, and then 1983 was an exceptionally good year for the Reagan administration. The economy came roaring back with a big positive shock, so we put the 0.038 in there so that we can see it. And growth rates pop up. That was followed by another good year with a 0.030, and growth rates continue to pop up again. And then that Reagan expansion kind of fades out for the rest of the 80s. Okay. Now what's going on here is I add each one of these, and I can go backwards and take them out if I do Control Z. Okay. Oops, that's where I changed that. Okay, so let's change that to a 0, and then a 0. You know what? I don't like this. Go back here. It's not going to let me. There we go. it's not going to let me. Let's leave that one like it is. And I'll format this axis so we can see it a little bit better. So we'll make that go from 6 to 10 instead of 0 to 10. Okay. And so we have that one shock there, and the effect of that one shock is we have these average growth rates of 0.035, and then we have the single negative shock, and it takes a while for our growth rates to come back to the 0.035. But in the real world, we don't have shocks in isolation. They're followed by another one like this, okay? And now what we're observing here and later is the combination of the two shocks, and you can see it still takes some time for it to come back to 0.035. Oops, don't know why it's got that highlighting there. It's like there we go. My mouse was kind of hung up on highlighting those things. Why is this not being responsive? There we go. So that becomes the 010. Okay, and again, that changes. I think the batteries are dying on my mouse here. I just clicked the little battery button. Okay. We go to here and we add in our other negative shock, 048. And then here, 0.038. And then here is 0.030. Okay. And so what we're seeing over here is the evolution of these growth rates, but they're still shocked growth rate on top of shock, and the shocks are adding up and they're all overlapping each other. And as long as I can get them in isolation, eventually we return to 0.035 down here. Okay, and the effect on levels up here is to have a couple hiccups in the levels. The effect of growth rates up here is to have some recessions followed by a strong expansion there. Okay, so this AR1 model that we have here is capable of picking up some pretty detailed responses to shocks in an accurate way and in a parsimonious way. Okay, parsimonious is the word that we use to describe a simple model that is fairly readily digestible just by looking at it. Okay, it doesn't have a lot of variables and a lot of contradictions in it. It's pretty straightforward. So this is a basic workhouse model for thinking about how the U.S. economy operates, and we're going to use this to think about the size of shocks that we're getting in 2020 with COVID-19 in the next couple of videos. Bye.